All right. Second to the last unit. Electromagnetism. Quantum. Quantum be the last unit. Quantum and nuclear. I got a ton of magnets. I got a lot of magnets. You've seen the magnetic time thing where like boop boop. It's a magnetic hourglass. So that's over here hanging out, chillaxing right there. Chillaxing and stuff. I have magnetic putty. This is a strong magnet, really strong magnet. It's the ball stuff. Here, magnetic putty. So got some magnetic putty. I'll just put it right here. You can watch what happens to the magnet eventually. Magnetic putty absorbs it. It's pretty cool. I got these guys. These are magnetic snake eggs. They stick together, and the idea is they make crazy noises.
Oh, I have those.
Question? No. Good question. Cool. These are cool. I got some ferrofluid. Ferrofluid is tiny, tiny magnetic field particles, or magnetic particles that are stuck in an oil, and that oil is suspended in water. And when you put a strong magnet up to the ferrofluid, you've probably seen ferrofluids on YouTube and stuff. Boom! You get really neat patterns. I'll just leave that right up there. You can take a look at it later. Okay, so we're talking about magnetism. Where do magnets come from? What do they do? What's a magnet? Yeah.
I used to keep things on my fridge.
Yeah, most of us know a magnet when we see one, but most of us don't know what's really going on in a magnet. Let me plant a seed for something we're going to talk about tomorrow. I have a whole bunch of little steel balls. The steel balls are not magnetic, and but this is pretty good magnet. And I have a copper pipe. Copper is not magnetic. Steel ball, not magnetic. So steel ball will stick to the magnet pretty easily, but the copper is not magnetic. Now, look what happens when I drop the ball down the pipe. Okay, you're just gonna you have to trust me to the floor down there. How long did that take? Like less than a second, right? Down it goes. If we used our kinetics equations, we can determine exactly how long it takes. So that's just a ball. Now I'm going to take the magnet and send the magnet down. Count how long it takes to go down. Ready? Did it get stuck? It did get stuck. Okay, let's try that again. It shouldn't get stuck. It's a lot bigger than the pipe. Let's try that again. There it goes. I put it in all cockamamie and put it in flat. Let's try again. If you're curious, that's how big the magnet is compared to the pipe. And it never got stuck. It goes down the pipe. Take that sweet little time. Won't that bother you? So if you're concerned about it getting stuck in the pipe, I have circular magnets too, which actually make. Here we go. Here's a bunch of magnets that are a lot smaller, and they won't get stuck. nice spherical magnets. How about these guys? These are discs. They're a lot smaller than the pipe. Now, I know somebody in fourth grade actually knows what's going on, but what do you think is going on? Why does it take so long to go down the pipe? Yeah, copper is not magnetic, and it goes down like this. Weird, huh? Come here, little magnet. Okay, so we're talking about magnets, and when we talk about magnets, it's important we also talk about the electrons, because a magnetic field comes from moving electrons, and a magnetic field will cause electrons to move. And it turns out there's a pretty good relationship between a magnetic field and an electric field. They used to be two different fundamental forces, Gesundheit. They used to be two different fundamental forces. It used to be, people thought there was Gesundheit, electricity, and there was magnetism. But sailors knew that wasn't the case. Long before any scientists wrote it down, sailors knew right away that electricity and magnetism were related. Why? Exactly. They'd be cruising along in the Atlantic, fishing, and they'd have a compass, and every time there'd be a lightning strike over the boat, the compass would spin. It would go crazy. Well, we knew the compass was magnetic, and we knew the lightning was electric. So even before any scientist ever wrote it down, sailors knew that there had to be some inextricable link between electricity and magnetism. It turns out that atoms are chock full of electrons. And when those electrons move in just the right way, they create electric fields, and those electric fields can create magnetic fields. Oh, by the way, this question we're going to answer later on. What do traffic lights and vending machines have in common? Anyone have a guess right now? What do traffic lights and vending machines have in common? They both lose electricity. That is true. How does a vending machine know you put a quarter into it and not a nickel?
Size?
All I know is if you tie a string around
Size?
a quarter
So,
and then put it in, you can pull
How
it.
many, like,
Size.
it has?
Old one again. Interesting. Okay. So if I get some sheet metal and I stamp out a shape of a quarter that's the same weight as a quarter, and I drop that into a
No.
machine.
How many nicks it has and what size?
Oh, okay.
And like,
Interesting. We'll talk about why
I
that
was
is.
told that one time.
It's fine. So we'll talk about it. So we learned when we were very small that opposite charges do what? And like charges do what? Well, it turns out magnets work the same way. I have a magnet that has a north pole and a south pole. And if I take two magnets that have north poles and south poles, and I arrange them north-north, they repel. They're like, no! But if I go north-south, they're like, and they stick. Or if I go south-south, they're like, no, we won't do it! But if we go north-south, they're like, okay. So we know this. Okay. Now, if you have a magnet, north and south, if I was to take a hacksaw, I got a hacksaw right over there. If I was to take a hacksaw and I was to cut this magnet in half, what would I get? I get two smaller magnets. Would I get one piece of metal that's full of norths, one piece of metal that's full of souths, or would the magnet just cease to exist? Well, it turns out, if you cut a magnet in half, you just get two smaller magnets of the same strength. You just get two magnets. You get two magnets. You just cut it in half. You get a new north and a new south. So if I took this north pole and the south pole and I cut it, then I have to paint a south on the red part and a north on the blue part. Because then I would have a new north and a new south. I would have two magnets, each with a north and a south. Why is that? Kind of weird. You're supposed to tell us, Mr. Byers. Okay. If you looked at a magnet and you were to somehow zoom in at the atomic level, what you're going to see are little clusters of atoms that are aligned. Now realize, I'm going to make this really simple for the purposes of our discussion. There's some complex physics and chemistry going on. We're just going to keep it really, really simple. But if you were to zoom in at the atomic level, you would see in this magnet a bunch of atoms clumped together, and they would be aligned. Now when I say they're aligned, I mean they're spinning in similar directions. Remember the electrons, they move around the atom? This is the model part that's kind of weird. It means they're aligned. And not all of them are aligned. For every billion or so atoms, like iron, these are probably ferrite magnets made mostly of iron. For every billion iron atoms, 2 or 3 are aligned. There's not a lot of them that are aligned. You are representing the strongest magnet that could ever exist. You're all fixed in position, and you're all facing forward. If, when the bell rings, you're no longer facing forward, some people get out of their seat and they turn backwards, some people just go forward, they go to the left and right, some people are climbing over the tables to get out of the room, then you would be a randomized arrangement of material. But right now, emulating a solid, you would emulate the strongest magnet that could exist, where every single atom is aligned. We never get anywhere close to that. If we did, the material would probably fall apart. But that's how it works. If you looked at an unmagnetized piece of material, the domains would be what? Randomized. They'd be all randomized. They'd be pointing in every direction. And by domains, what I mean are clusters of atoms. A few billion atoms here, a few billion atoms here. Clusters of atoms.
So how come if every atom in an object is facing it, spinning the same direction, why would it fall apart, the material?
The material would basically crush itself. Yeah, there would be too many atoms being magnets and not enough atoms being the material. Does that make sense? Yeah. Okay, how do you unmake a magnet? What do you have to do to get the atoms to basically become random again? What do you have to do? Yeah, ring the bell, exactly. What do you have to do to stop emulating a magnet? Move around. So how do you make atoms move around? Heat them or force them. So to make a magnet, you expose it to a strong magnetic field, and that aligns enough of the domains that you get a permanent magnet. That's how they make these magnets. As the magnet is cooling down, while it's still a little warm, a little soft, they expose it to a massive electric field that creates a massive magnetic field, and it becomes a magnet. Then it cools down, and it holds those domains in place. How do you unmake a magnet? Do the opposite. Make a move. So to unmake a magnet, heat it up or give it a good whack, and it will randomize the domains. So you unmake a magnet.
So if you beat a magnet with a hammer, it's not make a magnet.
Yep. If you drop a magnet enough times, every time you drop a magnet, it'll become less and less magnetized. Heating it up is a great way to just completely ruin it. Yeah.
So when you like stick your screwdriver to a magnet and it becomes temporarily magnetized, are those atoms?
Yes. They are becoming aligned. 1 out of every 50 trillion are becoming aligned. Yeah. With them.
Why does that wear off?
Because the natural tendency of things is to move, and even though the atoms are a solid, they are still moving. A little bit, a little bit, a little bit. If you were to somehow get to a theoretical absolute zero, then they'd be a magnet forever, because they wouldn't be moving anymore. But as long as they're moving at all, they will unmagnetize themselves naturally. Some materials resist that. They stay magnets for a very long time. That's like iron and nickel and cobalt. These are called ferromagnetic materials. Once they become a magnet, they stay a magnet for a very long time. Okay, so just like what James was talking about, inducing magnetic fields, or inducing magnetic fields in materials, if you have a non-magnetic material, like a paperclip, you can induce it to act like a magnet by exposing it to a strong magnetic field. So if I expose my magnet to a strong magnetic field, that magnet is, or the magnet is going to create a field that's going to align some of the fields in the paperclip. And again, for the purposes of our model, we'll show them all aligned, but in reality, not all of them are aligned. I have so many magnetic toys. You've probably seen them. Ever seen one of these? The shake lights?
Yeah.
Question?
Yeah, so we were talking about how, like, when you're making it, it's like has this kind of cooling, then you do the magnet thing. And in like any metal, you said like it has a certain metal. Like in any metal, like if you make a paper clip, a lot of times do the same thing. Then would it be permanent magnet? Or?
No. The materials that can be magnetic, there's basically three types of materials. Simple. There's paramagnetic, ferromagnetic, and diamagnetic. If you're paramagnetic, then you don't respond to a magnetic field. So the ferromagnetic materials are those three in the middle: magnesium, iron, and cobalt. And then there's some crazy things like bismuth is diamagnetic. It actually it repels magnetic fields. You put bismuth in a magnetic field, it actually pushes the opposite way. Its atoms will actually align the opposite way to the field. But yeah, some materials just cannot be magnetic. And that gets into the realm of the chemistry. I'm not going to go into it here, but it has to do with the lone pairs of electrons on the material, on the atoms. If you remember your chemistry, electric configurations, up, down, SPDF, that stuff. So if you have enough atoms in the right, left electrons in the right configuration, you have enough lone electrons, then you can actually become magnetized. Okay, so we learned weeks ago that positive charges create field lines. What direction do positive field lines point? Positives point out. Has it been so long? You have a final exam in 4 weeks.
I'm sorry, what?
You have a final exam in 4 weeks. Positive particles point outward, and negative particles point, you can get this one. I don't recommend studying people who got that one wrong. Inward. Okay. Similarly, magnetic fields can be created by poles, and a north pole points outward. North pole points outward, and the south pole points inward. Just like positive and negative charges. So if you're close enough to the board and you can see the arrows in the diagram, which is the north pole? The left side or the right side? The right side. North pole's over here because the arrows here are pointing this way. They're pointing out that way, out that way, out that way. The south pole are pointing in. So the north pole's here, south pole's here. And you can connect them just like connecting a positive and negative charge. You can connect north and south poles. James.
So does it work kind of like, does the Earth work the same way like the North and South Pole? So why is it that our compass is
Why? Oh, because they're backwards.
North is,
Yeah. They're backwards. It's because they were invented in the northern hemisphere. They paint the back of the arrow. They paint the back of the arrow to point north. Yeah. Glad you mentioned that, because I was going to actually just about forgot that. We are going to talk about the Earth's geomagnetic sphere and magnetic declination. But so yeah, north pole points out, south pole points in, and just like with the north pole, south, or the positive and negatives, you can basically draw the arrows like this. Okay. How are we doing so far? All right. Hope you're not copying every little diagram down. Okay. So it should make sense that magnetic fields vary directly with the strength of the material. Okay. When a magnet is made with electric current, we're going to talk about this in a little bit. Then it varies with the current. There's actually a fun little formula that shows how it varies with the current. Doubling the current, doubling the magnetic field. And then they vary inversely with distance. But not just inversely with distance, because magnetic fields are a field strength, just like electric fields are electric field strength. How do magnetic fields vary with distance? Works the same as light and sound. With the square, yeah. They still follow the inverse square law. Double the distance, you fourth the magnetic field strength. Okay. Pretty much everything falls off with the inverse square law. Yes. There is a part of, I think, the strong nuclear force that falls off the cube of distance. But I'm not entirely sure. I remember learning about it, but I forgot about it. I know it exists. I know I learned it at one point, but I forgot. Okay. Any other questions before we move on? Cool. Okay, so James talked about the compasses and the magnetic field strength, and how our compasses basically point backwards. It's upside down. I don't know why. It just is. So there's my Earth spinning around. But yeah, pretend it's not. Anyway, the magnetosphere, the geomagnetic shell that circles the Earth, comes from the Earth's spinning magnetic core. The Earth is primarily nickel and iron, which are magnetic materials. So that spinning nickel and iron creates the magnetosphere. Magnetosphere is handy because it shields us from ionizing radiation. A lot of the radiation spilling out of the sun is extremely harmful. The ionizing kind is really, really bad. You know, as bad as UV is and X-rays, ionizing radiation is just nasty. These are particles that are charged that will actually blast away part of our atmosphere. It is one of the theories about the way Mars is the way it is because it doesn't have a fluid core, because Mars's core is solid. It doesn't have a magnetosphere, so it can't handle an atmosphere. And if there ever was one, it would have been blasted away a long time ago. Which is also why, when your kids visit Mars for vacation, when your kids take their kids to Mars on vacation, they'll still have to wear spacesuits. Even when Mars is terraformed, they're going to go out to a beach, they're still going to have to wear like a steel or an aluminum hat to protect themselves from all the ionizing radiation.
They have to wear tinfoil hats?
They'll have to wear tinfoil hats. Yeah, or maybe some sort of device they'll have on their shoulder to create a little magnetosphere of their own to deflect particles away. But yeah, Mars does not have a geomagnetic shield, so it can't actually protect the environment.
In theory, could you make a magnetic artificial field big enough?
Yeah, you could. Magnetic declination is the difference between true north and magnetic north. It has to do with the fact that the Earth isn't symmetrical. So true north is a little different. So axial north, or north spinning on its axis, and magnetic north, they're different, and then true north and magnetic north are different. Because the Earth isn't symmetrical. It just make it interesting for us. Question?
What if we had mutation?
It wouldn't be genetic. It would, I mean, if you could somehow recreate your body fast enough, like Wolverine, then you'll be okay. But you'd still have to eat, and the biggest danger, if something ever happened to our geomagnetic shield, our magnetosphere, would be to crops. Crops wouldn't be able to grow. They'd be destroyed rapidly. Think the beginning of Interstellar. Everything's a giant dust bowl. Okay, so televisions, old TVs, used to have these things called electron guns. Electron guns. And the way they worked is there was a piece of metal connected to, I'm going to borrow this chair for a second, connected to a very powerful capacitor, and that piece of metal would eject electrons, and those electrons would be ejected through a ring, and that ring would tell the electrons where they're going to go. And then that beam of electrons would paint a picture. It would paint a picture 30 times every second. Yeah, totally ancient. The only reason I still have it up here is because I can do this once a year, or twice a year if we talk about it in chemistry. I can take a magnet, and just like Joseph John Thomson, I can stick a magnet on the screen and make the little electrons go places. Whee! And shot myself. So yeah, what's happening is the electron guns are basically blasting, hitting the screen, and painting a picture 30 times every second. And there's a magnet in the back that tells them where to go. And through some crazy math, basically a wave comes in and says, change the magnetic field by this much, and it makes a picture. So you can watch Cheers, or The Cosby Show, or Friends. Anyway, I can basically use a magnet and cause those particles to go somewhere else. Go where I want them to go. If you have a magnet, if you have a TV like this, I strongly recommend you destroy it with a magnet. So go home and get order a really strong magnet online, or borrow one of mine and go home and just like paint on it. Tell your parents, it's for science. And your TV needs to be replaced. It's an energy hog. It's got tons of dangerous chemicals and it wastes too much energy.
Yay,
That's
television.
Magnetic fields are measured in Teslas. A Tesla is a massively strong magnetic field. So the bulk of electromagnetism, the reason we call this study electromagnetism is because, like sailors knew, electricity and magnetism are related. We used to say it's the electric force, it's a magnetic, or it's an electric phenomenon, it's a magnetic phenomenon. Now we say it's electromagnetic. Because moving electrons create magnetic fields, and changing magnetic fields move electrons. So just like when I shake my flashlight, here we go. When you shake my flashlight, the magnet shuttles between this coil, and the shuttling coil causes a changing magnetic field in the coil, which causes a changing electric field, and light turns on. The opposite is also true. I made this in, actually, I made one of these in middle school. This is my brother's. Boop. You can actually, when you get closer, you can actually see the sparks in here, because I'm pumping 13 volts in here. 8th grade, we made this.
Well, grade curriculum sure has changed.
Yeah, I actually emailed about 3 or 4 years ago. I emailed the principal of the school, the middle school that I went to, and said, can I get some plans that we used? And he's like, that guy retired 20 years ago. Oh well, yeah, middle school curriculum has changed. But what's happening here is I'm sending electric current into these coils. That's creating an electric coil, which is causing a magnet to move. Motor, generator. If we spun it fast enough, we could put our multimeter right here, and we could actually detect a changing magnetic field in these. We could turn our generator into a motor, and a motor into a generator. Okay, next. Any questions before I go move on to something else? This is where we get to the bulk, the meat and potatoes of electromagnetism. What's that doing? What's that doing? Why is that there?
Yeah.
That little black cylinder, that little nub on the end that makes the cord kind of ugly.
It's not as annoying because they can never fit that to any desk. You know,
Exactly. Yeah, you have to take into account you're gonna feed it through something. You're like, darn it, it hit that thing again. It's called the ferro choke, or a ferrite choke. Like a choke. What it does is it makes sure the message my computer is sending to the projector is the message the projector gets. And this is why. If you have a right hand, give me a thumbs up. Okay. What you've all just done, if you used your right hand, what you've all just done is the two-vector right-hand rule. DJ doesn't have a right hand, he only has a left hand, because the right hand is busy, apparently. So, if you've all done this, what you've done is the two-vector right-hand rule. Take a pencil and wrap your fingers around your pencil. Okay, like this, with your thumb directed towards the end of the pencil or the pen. Your thumb is emulating a direction of current in a wire, and your fingers are emulating the direction of the magnetic field in three-dimensional space. Everything from here on out, you gotta think three-dimensional. You gotta think three-dimensionally, Marty. Three-dimensional. Okay. If you were to draw a wire like this, a current-carrying wire like this, and you were to turn this wire and aim it into the board, we show it with an X. Into the plane. Okay? We pretend that the wire is like an arrow. And when something is directed into the plane, we show it with an X, like the back of a fletching of the arrow. If we took this same arrow and we turned it towards you, and it's coming out of the plane, we use a dot. Out of the plane. So, like those arrows that they give little kids at the county fair, the arrows that have a rubber stopper on the front, a little rubber ball on the front, so you can't like kill somebody with them. So imagine a 6-year-old is about to shoot you with a rubber arrow. You see a little ball. So when something's coming at you, it's a dot. When something's going away from you, it's an X. So far, so good? Okay. Let's first look at this one down here. The one that's coming out of the plane. Take your thumb and direct it out of the plane. What direction is the magnetic field going? It's going perpendicular to the flow of current, and it's going counterclockwise. So you would show the direction of the magnetic field to be like that. That is the direction of the magnetic field. It literally curls around the wire. Again, gotta think three-dimensionally. So the right-hand rule says if your current is going out of the plane, the magnetic field is going around it counterclockwise. Now, if you turn your thumb and you aim it into the plane, what direction is it going now? Clockwise. So it's going into the plane, it's going to create a magnetic field that goes that way. Now here's my favorite. If you have a wire that's running from left to right carrying a current, what direction is the magnetic field going? Out of the plane where? It's going out of the plane above the wire and into, out of the plane, thank you, other way. Out of the plane above the wire and into the plane below the wire. Pretty cool, huh? That's how the right-hand rule works, at least part of it. We'll get to the other part in a little bit. So back to our original question. Why is that there? Here's why. There are little wires inside that cord that carry the magic that the computer sends to the projector. The computer is sending a message to the projector in the form of little bits of current. Here's the problem. The projector is also sending a message back to the computer in the form of little bits of current. Each of those little bits of current is an electric field, and electric fields create what? Magnetic fields. And we learned in electrostatics that fields can interact. Fields can add and subtract. So you see where this is going? If you have a message going that way, and you have a message going that way, they're both creating magnetic fields. Those magnetic fields can interact, interfere. They can add together, and all of a sudden, the magnetic field that this one's creating is affecting the message from this one. And the magnetic field from this one is changing the message from this one. Does that make sense? So one message is creating a magnetic field that's changing the message of the other wire. I'm sorry, this is so boring. Try to hang in there. That's why it's there. What that is a magnet. You put a huge magnet around the wires and it says, I am so strong, your little magnetic fields cannot affect each other. It's the camp counselor to make sure the two wires don't affect each other. It's a big fat magnet. Yeah. It's a giant magnet that keeps the little magnetic fields that would be created from affecting anything. Yeah.
So that way they're all affected by that big magnetic field and that
Yep.
can be controlled.
The same way. Well, because it is a consistent, because it's a very strong, consistent field, it doesn't change with the message. As the message changes, as the message goes, it doesn't change the field. It's a big magnet. Sometimes it's called a shield. When you hear a shielded cable, if it's a shielded cable, it needs to have a magnet on the end of it. Yeah.
Why don't you put it towards the end where you plug it in? Why not at where it starts?
It could be anywhere. It could be in the middle. There's probably another one at the other end, just for convenience. But yeah, it could be anywhere in the middle. It's just it would be really hard to send the cord through a conduit. You get a big ferrite right there. But it could be anywhere. So that's kind of fun. Okay. Now, if you have a right hand and you give me the thumbs up, do this. Take your right hand with your thumb up, and take your index finger and point it straight out. Like pew 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 pew. Only don't go pew pew. Go pew 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 pew. Okay. Now take your other three fingers and turn them 90 degrees so they are perpendicular with your other finger. Now what you have, if you've had calculus, hopefully you've encountered the cross product and the right-hand rule with cross products. If you haven't had calculus, you can use the right-hand rule to figure out where cross products are. Maybe don't do that in calculus anymore. But so what you have is you have a thumb, and an index finger, and three other fingers that are all what to each other? They're all perpendicular to each other. This is the 3-vector right-hand rule. Your finger represents current or travel of charges. Pew, pew, pew. Imagine shooting charges out. Pew, 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 pew. Your 3 fingers represent the magnetic field, and your thumb represents a magnetic force. And the formula is QDB. QDB my kingdom for a black pen that doesn't stain the whiteboard.
Focus the bags, you're not a king.
I don't have a kingdom. You don't have a kingdom. So the formula is this. If you put a charge, Q, and a charge Q is traveling with a velocity v in a magnetic field V, it's going to feel a magnetic force dB. What I was doing with the magnet over there is I was introducing a magnetic field to that charge, and that charge was feeling a force that resulted in an acceleration on those electrons. So the magnet was creating a magnetic field, it was traveling with a velocity, the electrons have a charge, and they experience a magnetic force that eventually becomes an acceleration.
So that's the force of the current.
This is a force on a charge-carrying particle, which we're going to do current in a second. Okay, so what is the unit for force? Final exams in 4 weeks. Newton, yeah. It's not a trick question. What is the variable for charge? Coulomb. What is the variable for velocity? Meters per second. And the variable for magnetic field strength? Tesla. Okay, so there we go. A Newton equals a Coulomb times a meter per second times a Tesla. It means so many things. There's another formula. And this is the formula when a current-carrying wire, current is still I, of length L finds itself in a magnetic field B. A current-carrying wire in a magnetic field will still feel a magnetic force. Only that current-carrying wire feels a force that varies with the current in the wire and the length that's in the field, and then the field strength. I'm glad you asked. What's the unit for force? Newton. What's the unit for magnetic field strength? Tesla. What's the unit for length? Meter. What's the unit for current? An ampere. And we know an ampere is a coulomb per second. Exactly. An ampere is a coulomb per second, so we're going to replace that ampere with a coulomb per second, and do you see how they're the same? Newton, coulomb, meter per second, Tesla. Newton, coulomb, meter per second, Tesla. Same formula. Very cool. So these two things represent the same thing. Whether you're talking about a charged particle traveling with a velocity or a current traveling in a magnetic field, they're still going to feel a magnetic force. Next question. Who amongst you lives near a power line that hums? So sorry. You're going to die. Probably in 70 or 80 years. The power line will have nothing to do with it. Because it doesn't do anything. But why does a power line hum? Because it's vibrating. A power line, exactly right, is vibrating just like a guitar string. And some of you might even know the frequency that power line is vibrating. What is the frequency that power line is vibrating? I'll give you a hint. It starts with an X. It starts with an S and has an X in the middle.
60.
60. It vibrates at 60 hertz, which, not coincidentally, is the same as our AC power. This is what's happening. That power line sits in Earth's magnetic field. You know Earth has a magnetic field? It's a giant magnet. Hopefully we've covered that by now. Okay, so that power line is sitting in Earth's magnetic field. When a positive charge, a positive current, is traveling down that field, it's going to feel an upward force, upward FB. 1/60th second later, a negative charge travels through that field, and it feels a downward FB. And what you get is a guitar string, where that thing is going up and down and up and down and up and down 60 times a second, just like a bass guitar string. Boom, 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 boom. Only it's the Earth and the current that's going constantly forward and backward and forward and backward. Positive, up, negative, down, up, down, up, down, up, down. It's a guitar string. So next time your parents drive by one, they're like, that's going to give me cancer. You're like, no, Mom, it's not. Totally normal.
Can't give you cancer, just so you know.
Or you can do what I do. It's like, you're going to die, Mom. You lived here for a lot longer than I have. You're going to die. Way sooner than me. You probably only got 40 years left. Okay, so, three-vector right-hand rule. These fingers are the magnetic field. That's the current. That's the force. Moving right along. Okay, so take a look. If the current is up and the force is to the right, where's the magnetic field? If the current is up and the force is to the right, where's the magnetic field? Out of the plane. And we show out of the plane with dots. Yes, you can just wait. If the current is up and the force is to the left, where's the magnetic field? It's into the plane. And we show that with X's.
Because you turn your hand.
And you have to use a right-hand rule. You have to use a right hand. It doesn't work with a foot. Now here's the other thing. This is for, listen very carefully, this is for positive particles and current. because by convention, current is the travel of positive particles. This is for positive particles and current. What I'm not supposed to teach you is if you use electrons, you can use your left hand, because electrons are negative. I'm not supposed to teach you that. I'm supposed to teach you that electrons, you just use the opposite direction of force. You curl your thumb down for electrons. Yeah, I'm supposed to teach you that if this is for positive particles, you curl your thumb in, that's for negative particles. But it turns out to work, you can use your left hand instead. Question?
Is your finger the current or the force?
Yes. Your finger is the travel of charged particles or current. Your three, you usually almost always show the magnetic field with lots of arrows or dots. So you usually use 3, so 3, and then thumb is force. Okay, I guess we'll pick this up again tomorrow. We'll do these tomorrow. Oh, I forgot to pass out your tests.